This lecture discusses application of pulse width modulation, abbreviated as PWM. A PWM signal has a fixed period, that is, its frequency is fixed. However, the high pulse width can vary. We use this varying pulse width to modulate either voltage or current through to an external device. For example, if we apply a PWM signal to an LED, then what is going to occur as the pulse width increases, more current is delivered to the LED and it will become brighter. As you decrease the pulse width, less current is delivered to the LED and it becomes dimmer. Recall that the ratio of the high pulse width to the period is called duty cycle. This graph plots LED current versus the duty cycle. Notice that this is a linear relationship. This is nice. This means that we can, via PWM signal, we can linearly control the brightness of this LED, and actually this linear relationship works for many other devices as well. We're going to experiment with PWM by using the output compare module to generate this PWM signal, and we'll control the width of the PWM signal by reading a voltage generated by a potentiometer via the PIC24 ADC and allow this voltage to control the width of the PWM signal. So what will happen is that as we change or lower this voltage, this pulse width will increase and decrease. Let's review how the PWM is generated by the output compare module. The period of the PWM signal is controlled by the period of the timer that is used for the output control module. Whenever the timer reaches its max period and wraps around, the PWM signal will be set high. At that point, it will remain high until the timer value matches the value in the OCR register. At that point, it will be set back low. Let's look at some code that accomplishes this pulse width modulation of the LED brightness. We're first going to configure timer 2 for a periodic interrupt. That's going to be equal to this period, which is going to be 20 milliseconds or 20,000 microseconds. We're also going to configure the output compare. We'll first disable the timer. We'll map OC1 to reconfigurable pin 14. That's where our LED is going to live. Now we're going to write a value of 0 to the OCRS register. Notice that this is the OCRS register and not the OCR register. In PWM mode, we write to the OCRS register, and the PWM module itself will transfer this value at the correct time to the OCR register. It does this to avoid glitches in the PWM output. So again, we repeat, we'll be modifying the OCRS register and not the OCR register. We're then going to configure the output compare control register. We'll select timer 2 as our source timer, and then we'll configure it for PWM mode. So we wrote a 0 to the OCRS register whenever we configured the output compare. This means that the pulse width is 0. The output signal, the PWM output signal, is always 0, so it'll be initially off. Eventually, we have to write a non-zero value to this register in order to get a non-zero pulse width. When is that going to happen? That's going to happen inside the interrupt service routine of the timer 2 interrupt. When this timer 2 interrupt occurs, the first thing that we're going to do is we're going to clear the timer 2 interrupt flag, and then we're going to read the converted ADC value that's sitting in this special function register. That's going to be a 12-bit value, which means that it's going to vary between 0 and 4095. We're going to store that in a 32-bit temporary register. We now want to map this somehow to a pulse width. How are we going to do that? Well, we know that the pulse width is going to be proportional to, the period is proportional to PR2 plus 1. So what we're going to do is we're going to take this ADC value, which ranges between 0 and 4095, divided by 4096, and multiply that by PR2. That way we'll get a percentage of PR2 as our new value, and we're going to write that to this OCRS register. When we do this computation, here's how we're going to do it. We're using a 32-bit value here for extra range. Instead of doing the division first, since this is integer, if we divide it by this, we'd always get 0. So what we're going to do is we're going to multiply by PR2 first, and then we're going to divide by 4096. Well, dividing by, since these are unsigned values, dividing by 4096 is the same as shifting to the right by 12. So this line right here does this computation of PR2 times the ADC value divided by 4096. So once we have that value, we're going to write it into our OCRS register. Even though this is a 32-bit value, only the last 16 bits are actually significant, and that's what's going to be copied into this OCRS register value. Before we leave, we have to do something very important. We need to make sure that the ADC is converting the next value so that when we come back into this ISR, the ADC has a new value for us. So we'll call this macro right here that's going to start the sampling and conversion before we leave the interrupt subroutine. Once we come back in here, our ADC will have our new value ready to be read. This is the main code for our Led Pwm example. We're going to call config basic. We'll config timer 2, configure our output compare module. Our potentiometer is connected to the AN0 pin, so we'll make sure it's an analog function. We'll config the ADC as we did before. Use AN0 for analog input, 31 clock sampling, 12-bit mode. Right here, what we'll do is we'll start the ADC sampling and conversion so that when the first interrupt occurs, it will have a value ready to be read. We'll then turn on the timer. Once the timer turns on, then the PWM signal is being generated by the output compare module and the interrupt subroutine that is updating the OCRS register. This while loop right here, all it's doing is printing out some informational messages to what the PWM pulse width is in microseconds. It does this by reading the OCRS register, which is being updated by the timer interrupt service routine, uses the ticks to microseconds conversion function to convert this to microseconds. We store this in this variable right here, and then we use a formatted print statement to print that out. This delay statement right here simply keeps these lines from being printed out too fast. Here's an example of the program running. We see the pulse width out of sight. I'm adjusting the potentiometer value. I'm making the voltage higher. Pulse width is increasing. Now I'm going to lower the input voltage. This trace right here is the input voltage on the pin. Notice it's lowering, and as I lower the voltage, the pulse width in Bully Bootloader goes lower, and the pulse width becomes narrower. So this is simply demonstrating the code running on the PIC24, and so you can see how pulse width modulation is operating. Another application of pulse width modulation is DC motor speed control. DC stands for direct current. Let's take a look at what we have here. We have a DC motor. It's going to be connected to VDD through here. Let's trace a path. It's going through this switch, through this DC motor here, through this switch, to this power MOSFET. What is this MOSFET? We're just going to treat this as a switch, and this power MOSFET as a switch can either be open or closed. When it's closed, we'll have a path to ground. When we have a path to ground, it means that current will flow through this DC motor, and when current flows through the DC motor, it will spin. Now, what are we going to be using to open and control the switch? We're going to be using a PWM signal generated by the output compare module. So this PWM signal, when the pulse width is high, the switch will be closed, and when it's low, the switch will be open. And so what we'll be doing, we're opening and closing the switch very rapidly. And just like with the LED, by opening and closing the switch very rapidly, we're going to control the average current that's flowing through this motor. The more current that flows through the motor, the faster it's going to spin. The less current, the slower it's going to spin. So the pulse width here is going to control the average current, which will then control the average motor speed. What about this other set of switches here? What are they for? Well, let's put this switch in this other configuration. We'll put it there, and we'll put this switch there. Now let's trace a current path from VDD. We're going to trace through here, through there, back around through here, and to the MOSFET. What's going to happen is this will reverse the current flow. When we reverse the current flow through these switches, the motor will spin in the opposite direction. So this set of switches here and this parallel I/O pin here is for controlling the direction of spin of the motor. This diode here is called a snubber diode, and it's helped to suppress voltage spikes that can occur in this DC motor when we interrupt the current control. Remember, this thing is a switch. A motor looks like an inductance L. The voltage across the inductor is equal to L times di dt. This is the rate of change of current across this inductor. Let's assume that this diode was not there. If it's not there, then we have current flowing through here, and when we open the switch, all of a sudden the current flow has nowhere to go, so the current flow drops to 0. That's a big instantaneous change in current, and we're going to generate a big voltage across this inductance. So how can we avoid this? Well, what we need is we need somewhere for this current to flow when this switch becomes open. By having a diode here, we provide a path for the current to flow through this diode and back into the motor, and it will dissipate itself this way and snub that voltage spike that would ordinarily occur. A half-bridge driver is an integrated circuit that takes all of these electronics here and integrates them into one handy package for controlling the speed and direction of a DC motor. A TI SN754410 quad half-H driver allows us to control both the direction of the motor via these two pins here, 2A and 1A, as well as the speed of the motor via this pulse width modulated input right here. It has two separate supplies. It has one supply, 4.5 volts to 5 volts, for the logic that's inside this integrated circuit, and it has another supply that can go between 4.5 and 36 volts for the DC motor itself. This would be the high current supply that would be needed by the DC motor. Another application of pulse width modulation is to control analog servos. Servos are widely used to steer model cars, airplanes, and boats, and they consist of a DC motor with gearing that reduces the output speed and increases the output torque, and a control circuit that spins the motor until the motor's position, as measured by a potentiometer, matches the desired position specified by a pulse that is sent to the servo. So you can see that this is the external of a servo. This is called the horn, where you attach control arms that might be attached to flaps in an RC plane or whatever. While inside you have the DC motor, you have the potentiometer that's going to measure the position of the DC motor, and a digital control circuit. For analog servos, they have 3 wires: power, anywhere between 4.0 and 6 volts, black is ground, and a signal wire that's going to be used to specify the position of the servo, and the signal wire is going to contain the PWM signal that's going to be used to specify the position of the servo. An HS311 is an example of a typical analog servo. It has a servo arm. When it's pointing just straight up like this, we'll call that the neutral position, the 0-degree position. To move it, we can move it fully 90 degrees clockwise or fully 90 degrees counterclockwise. To do this, we're going to send it a PWM signal that has a period of 20 milliseconds, and the pulse width will control the position of the servo. A pulse width of 2.4 milliseconds or 2400 microseconds will mean that the arm is rotated 90 degrees clockwise in this position. A pulse width of only 600 microseconds or 0.6 milliseconds will mean that the arm is rotated 90 degrees to this direction. Not all servos can cover this entire range. With some fairly minor changes to the LED PWM code, we can convert that code to actually control the position of an analog servo. Our PWM period remains at 20 milliseconds, but now we have this min pulse width of 600 and max pulse width of 2400, and we're still going to read the ADC in the timer ISR, and we're still going to update the OC-RS register. The only thing we'll do here is we're going to now take this ADC value and map it to a pulse width that's going to vary linearly between a minimum of 600 microseconds and a maximum of 2400 microseconds through this equation right here. So with this code right here, we could use the external potentiometer to control the position of the analog servo.